All right, guys, welcome. Is everything visible to you guys out there in Zoom? You can see back here pretty good? Great. I'm glad to see all of you today again. I hope you had a good weekend and hopefully the studying is going well. Yeah, so if you haven't had a chance yet to try a sample exam, there are two of them in Canvas in the resources folder. You can pick one of them and just like later tonight, sit down, just give it a try. Get, if nothing else, just to get yourself kind of in the rhythm of what taking the test would feel like. Because sometimes students can be very well prepared, right? They did a lot of studying, they've seen many examples, they're ready to go. And then just being in that test environment is just it's not comfortable. So one way to sort of head that off is to try to put yourself into that context. So I've got a couple of those sample midterms. Both of them are solved as well, so you can check the solutions afterwards. But I would try at least one of them almost as if it was a real exam. Like don't be goofing off and like watching TV and talking to 5 people. Just like try to quietly spend an hour and 15 minutes and just work through that as best you can. And then tomorrow, you can ask me some questions. I'm going to come in the morning. I don't have a lot of office hours before class because I have a lot of classes before 4 o'clock, but I will be here every minute that I can be. So especially from 12 to 2, it's a good time to catch me on a Tuesday. You can also shoot me emails. You can also talk to each other about it, and of course use my solutions in the Canvas resources as well. So yeah, so hopefully that'll be a good way to kind of do your final touches on your studying. On Friday, we went through these review session problems for a couple hours, and we got about halfway through them. There are 10 problems here. I sent out a link, a YouTube. Did everybody get the email on that? So there's an email with a link to all of those problems that we did on Friday. My plan for today was to start with the ones that I did not do that are from that same handout. And if we get through all of those and anybody's here who wants me to, I can go back to the ones we did on Friday and give you a second pass through on them. But I think most of you probably could either watch the video or just read the solutions as well. So anyway, does that sound like a game plan? Okay, so with that in mind, let me see where I left off last time. Actually, I want to make sure that I cover certain topics as well. Let's just actually start with number 2. So again, I'm starting with number 2 because I did number 1 on Friday. So I'm picking examples that I didn't do. These are not in order though, from any other time. So here we go. So number 2 just says, let capital X and capital Y be sets. This is not a very good marker. Can you throw this away for me? Thank you. So with, that's better. The size of X equal to 4 and the size of Y equal to 7. And I just want to ask a series of questions about this right here. First of all, I want to know how many functions there are from X to Y. So how many functions, I'll call them F, that goes from capital X to capital Y are there? And then we'll tweak the question with some follow-ups as well. So how many functions can we make from one set to another? So it's a combinatorics question, but at the same time it involves functions. So the thing you're counting is actually a very mathematically motivated source. Any thoughts on how we might approach a problem like that? Yes, Christian.
You could start with the Cartesian product of the 2 sets, but then we want to get rid of any if something's a function, every output has exactly 1 input, so we want to get rid of some of the inputs of the Cartesian product.
So the Cartesian product would be ordered pairs.
Yes.
something from X and something from Y. What would be the size of that, by the way? I'm just curious. 4 times 7, so you'd have 28 of those. So we'd have 28 ways of making pairs. It might even be helpful if we write down some notation for these sets. So I could say X is maybe A, B, C, and D, right? And Y is 1, 2, 3, 4, 5, 6, and 7. And so F has to take each of those 4 letters and spit out an output here, right? So the 28 pairs in X cross Y, the Cartesian product would be, A1, A2, A3, A4, and so on, right? B1, B2. Okay, so, but we do have to understand that a function from X to Y has to have every input represented. There has to be f of A, f of B, f of C, and f of D. So like this by itself isn't a function from X to Y, right? You're assigning you're saying I'm going to send A to 3. That would be part of making a function, but it wouldn't be a whole function. So we either have to be more clear about how we're going to use the Cartesian product to make a function, or we need to scrap this and try something else. So let me draw this a little more visually. Let's draw the set X like this, where we actually put the 4 input elements, the domain elements there, and then we make another set Y here with the numbers from 1 through 7. And see, a function F is an entire picture of domain, codomain with arrows now, right? So we're going to assign each input to an output. And we have to think about how many ways there are to do that. And thoughts here? Jasmine?
Would it be 7 to the 4th?
7 to the 4th. So how are you coming up with that?
Because each input would have 7 choices to map to.
Okay, we can imagine that each input chooses an output. So A might choose that output, and then B might choose that output. And since there's no constraints here, 2 different inputs could choose the same output. That would be fine, right? So there are 7 choices for each of the inputs. And so for the solution, I'm going to go back here, and maybe I'll actually try to write this in a different color. For the solution, we could just say each input from capital X has size of Y, which is 7 choices. Independent, so there's an independence here of every other input. So it doesn't matter what we do with any other input. And so we can use the multiplication principle effectively and just say, well, the subtasks are to assign where A gets sent, where B gets sent, where C gets sent, and where D gets sent, and we have 7 choices for each. So by the multiplication principle, you can abbreviate that MP if you would like. We have 7 to the 4th choices. Well, let's just say functions. 7 times 7 times 7 times 7. So what we've done here, and I want to talk about this for a minute, is we have taken each input element and assigned it to an output element, which makes natural sense. Like that's how you would create a function. You would start with the inputs and then assign them to outputs. My question for you is, could we have turned that logic on its head and instead started with Y? And for each of these 7 elements, could we have thought about how many choices there would have been to assign something to it? Would that have worked? And that would have been a different, well, this is 7 to the 4. This 4 to the 7 is a different answer than 7 to the 4. So there must be, and this is correct, by the way, what we've got here. So what's wrong with 4 to the 7th? Like,
It
why
won't do.
can I not just take each of these 7 elements and sort of imagine what would have gone to it? So, well, there could have been 4 things that went to it.
Yeah,
What's wrong with that reason?
and then it wouldn't be a function.
Okay, it might not be a function. What if all 7 of these elements had a pre-image that was the same thing over here, right? That's, you're not allowed to have 2 arrows coming out of the same dot on the left side. So, you know, the problem would be if I was going down the line saying, well, for each of these elements, how many choices are there? My answer would be, it all depends. I wouldn't be able to give you a quick answer. Actually, you don't have to have anything mapping into this one, right? This could be a codomain element that's not in the image of the function. It's not like you have to find an A, B, C, or D to send it to that one. So you might not have any choices. On the other hand, let's say you do pick a pre-image for one and you choose A to be a pre-image for one. Okay, that's fine, but then the issue would be, then that affects what 2 can do. Because 2 would then not be allowed to also have A as a pre-image. Okay, so then 2 would have to pick something else, it would have less choices, or maybe again, maybe 2 doesn't have a pre-image. The issue is though, that we don't have independence of choices, right? What pre-image the first element has would affect what pre-images the second element could have and the third element and so on. And because of that, you would create a lot of messy cases out of this scenario if you tried to reverse engineer it. In the same way that if the fires are choosing the fire trucks and the first fire chooses the blue truck, well, then the second fire cannot also choose the blue truck because the blue truck can't be fighting 2 fires and in 2 different places at once. So you can go back to some of those earlier examples we did and try to understand why is it that it has to be that the fires are choosing the trucks rather than the trucks choosing the fires, that kind of thing, right? Because I think some people have been having some issues with that.
I was trying to think of it, like, would you ever, like, how would the question change if it's been like, 7 choose 4 and then multiply it by 4 factorial to pick its, like X elements? Could you ever do something like that?
That would leave out the functions where all of the inputs go to the same output.
Yeah.
So so the question, if in case you couldn't hear that in Zoom, somebody was asking if you thought of it as I'm going to take 7, choose 4. I'm going to choose which 4 of these elements of Y actually play the game of being part of this function, right? And then you have 4 factorial ways to take A, B, C, and D and map them to those 4 elements. That would be great for a function that is 1-to-1. I think you're getting to the next, this is part A. So I think we're getting to the next part of this problem, guys. Are there questions though on this first part? Okay, let's move on to part B since it's already been kind of proposed here. The question is how many 1-to-1 functions f from X to Y are there? 1-to-1 means that 2 different inputs cannot go to the same output. So how does that change our solution here? Instead of 7 to the power of 4, what would change about this, the choices that we have along the way here? Yeah, Maddie?
Don't we have to choose and then order? So we would do 7, choose 4.
Okay, so you're going with what Nikolai is saying, which is choose the 4 codomain elements that are going to play the game first. You can certainly do that. So there are 7, choose 4, right? Ways. And again, try not to, you don't need to simplify this number. Just leave it as 7, choose 4. If it was on the test, I'd prefer it like that, right? Ways to choose 4 outputs in Y to be used. And I need to use 4 different outputs. Otherwise, this function won't be one-to-one. Okay, so I choose those 4 outputs, and then what else do we have to do then?
You gotta order it, so
Then there would be 4 factorial ways to assign A, B, C, and D to those 4 outputs. Okay, so next we assign those 4 outputs to A, B, C, and D respectively in 4 factorial ways. All of this has to be explained. Okay, so you're seeing me do these write-ups. I'm trying to really write them up the way I would hope to see them. I don't have to see exactly this write-up. I don't have to see exactly this write-up, but I have to see more than just 7 choose 4 times 4 factorial. If you write that down, not gonna be too happy with that.
Dr.
Okay,
Annan,
yes.
just real
Zoom.
quick, this
Yeah.
is not like, I would not solve it this way, but you are able to solve it if you take all the functions that are possible. You subtract out the ones that are
That
onto,
are
and then
not one-
take out the ones that are bijective, right?
That would not be adequate. Because there are some functions that are neither. There are some functions that
Oh,
are
you're
not
right,
one
you're
to
right.
one, not onto. So if you take all functions and you remove the bijections and remove the onto ones, that does not leave you with the ones that are one to one.
Right.
Because
Exactly.
it also leaves you with some of the ones that are actually neither.
Mm-hmm.
So I would not use the subtraction
Gotcha.
approach on this one. I would go with a very direct approach. But the one thing we still do need to do here is by the multiplication principle, right? We finish up the task of making this function by doing the multiplication of these values. So we get 7 choose 4 times 4 factorial ways to make a one-to-one function. Now, having said that, I have to be honest with you that this is not really the way I think about creating a one-to-one function. The way I think about doing it is not that I choose my 4 outputs, but rather I just go through A, B, C, and D. And then I have 1 through 7 here. And all I do is I just say, all right, start with A. I have 7 choices for where I send A. And then because I can't use the same output twice, B only has 6 choices, right? And then C only has 5 choices, and then D only has 4 choices. So you could also have given that justification. So as an alternate solution, I won't write out too long on this one, but we can just say there are 7 choices for the image of A. Guys in Zoom, if you're having any trouble reading my board, be sure to let me know. I'm trying my best to keep the camera clearly focused on it, but if for any reason it's not showing up, let me know. Then 6 choices for B, and then I'm just going to say etc. And so then when you multiply those together by the multiplication principle, you get 7 times 6 times 5 times 4. Which you could also write as P of 7, 4, which is permutations 7, 4. But I'm fine with 7 times 6 times 5 times 4. Which, by the way, of course, is the same thing as doing this. Right. Yeah.
So my brain immediately went to this
Okay.
in part A though.
Uh-huh.
So when you just have how many functions from X to Y, it's totally generic.
Mhm.
There's no one-to-one assumption, there's no.
Don't assume anything that's not stated. Right, exactly. So we don't want to assume anything more than what the question's saying. Yeah. Okay, let's do a third part here. So I'm gonna go to part C. It's actually 4 parts to this question. So part C is going to be really fast. And it just says how many functions G, which goes from Y to X, are there?
That's what we did the other way around for when we were discussing part A. It's just instead of,
Exactly. So what
yeah.
would the answer be? 4 to the 7, great. So I won't even spend any more time on that. Basically now, each of these 7 inputs over here has 4 choices for an output. So you're switching the roles of the 4 and the 7. But there's a reason why I asked that question, which is so I could get to part D, which is just now how many onto functions G from Y to X are there. Why didn't I ask you how many onto functions there are from X to Y?
The Y number of things that we have in Y is bigger.
Yeah, Y is bigger than X, so you actually can't make an onto function that goes from X to Y. Right? If the codomain is larger than the domain, you have 0 onto functions. So that would be a non-combinatorics question. I mean, it's obviously a good question, but it would not be a Math 471 question. But this one would be, because it is possible to have an onto function from Y to X, because in this case, the Y is larger than the X. Okay, so let's think about part D. Any thoughts on how we could count the onto functions? Here's, now we're putting the Y on the left side. 2, 3, 4, 5, 6, 7. And we're putting the X over here with A, B, C, and D. And we're trying to create our function G going this way now. So do we have any thoughts about how many, or how, maybe not what the answer is yet, but how we could approach this?
I think it might be like inclusion exclusion, because like when you have an onto function, everything in the codomain, you might not be using it. So then you have to like set up cases where like you don't use A, you don't use B, C, etc.
So if we don't use A, if we don't use B, if we don't use C, or if we don't use D, then it's not onto. So you're talking about functions that we don't want to count, which means what technique are you really referencing here?
Subtraction.
Subtraction, right? That's actually subtracting violations, right? So we could take all functions, which we've already figured out, and subtract violations, which is what I'm going to recommend that we do here. This one is sort of best done by subtracting violations. If you try to count this directly, if you say, oh, I want to count the onto functions directly, then you run into the same problem again that, okay, if you get through the first, 5 elements and you chose the same A for all of them, then now all of a sudden you don't have as many choices to finish this function out. With the last 3 elements would have to go, I'm sorry, the first 4, let's say the first 4 elements all got mapped to A. Now you must send 5, 6, and 7 to B, C, and D. I'm talking about if we were trying to directly make onto functions rather than subtracting violations. I'm trying to convince you that this would be difficult to do. Because if we said, oh, first element has 4 choices, second element still has 4 choices, third element still has 4 choices, fourth element still has 4 choices, then how many choices you have after that would depend on what choices you had made here. If A, B, C, if 1, 2, 3, and 4 all chose the same output, then 5, 6, and 7 don't have total freedom anymore, right? But if you started off differently and the first guy has 4 choices, the second guy has 4 choices, the third guy has 4 choices, and the fourth guy has 4 choices, and if they choose like that, well, now the 5th, 6th, and 7th elements can do whatever they want because the function's already for sure going to be onto. You don't have any constraints imposed. So whether there are constraints and when they start taking effect and how significant those constraints are is going to be depending on how the choices were made in the beginning. And that becomes messy to count directly, right? Guys, if it sounds messy, if you're starting to work out something and it's like, yeah, this is really going to be a whole page of messy cases and dependencies and so on, I want you to put your pencil down for 30 seconds, take a breath and ask yourself, is this really the easiest way to do the problem? I could make a combinatorics problem for you that would take you 1 hour and 15 minutes to solve it if I really wanted to. I could like have a million cases and create some horrific thing, right? You have to trust me. That's not what I'm going to be doing on this exam. I want to see you demonstrating your knowledge of the different tricks, like the subtraction trick, inclusion, exclusion, all of these kind of things. And so chances are, right, because unfortunately, there's going to be problems that I write where you can approach them in a way that might not be wrong, but which is so messy that you would spend the entire exam just doing one little problem. So try not to do that. Try to pull yourself back, take a breath, and ask yourself, if I was Dr. Annan, is this the question I really would want my student to answer? Right? If you can't honestly say yes, if you're like, yeah, there must be some other way to think about this, give yourself permission to do that, or at the very least, maybe go on to something else, and then maybe come back to it with a fresh mindset. Yes.
So would it also work to not do subtraction trick, but do like 7 choose 4 and then permute, or not permute, but yeah. 4 factorial times 4 factorial for which options they go to. And then multiply it again by the last 3 going to any of these 4 choose 3.
Okay, I'm not sure if you guys all heard that in Zoom. Nikolai had a suggestion for a way to solve the problem, and I would like to get everybody's input on this. What he said is, let's make sure that this function is onto by choosing 4 of the elements from the domain that are for sure going to hit 4 different outputs, which are the outputs A, B, C, and D. Let's do that first, right? Let's make sure that this thing is onto by taking 7 choose 4. And of course, once we've chosen these 4, there would be 4 factorial ways to decide who gets which output, right? And then after that's done, I have 3 more elements that did not get chosen initially. And because we've already made sure that it's onto, we can assign those other 3 elements willy-nilly however we want. 4 choices, 4 choices, 4 choices. What do you think about that reasoning? Would that work?
It sounds right to me.
Sounds good?
It reminds me of the one more problem where we had like the 3 different kinds of drinks, the one lemon, the one lime. And
Oh, the lime and lemon drink problem.
Yeah,
Uh-huh.
Yeah, where lime and lemon go, and then orange go.
Right. That was a little different just because the lemon and lime drinks, those were really subtasks that were independent of each other. Like, so, you know, you have to pass out the lemon drink, certain number of ways to do that. Then another certain number of ways to do the lime drinks. After that, then for sure 2 people have drinks already, and you just need to make sure that whoever didn't get a drink so far gets one of the
Yeah.
regular drinks. I
Yeah.
forget what it was. And then you're using the multiplication principle. So let me explain why Nikolai's reasoning here is not going to work. We cannot just pick 4 elements from the domain. Let's say I picked the first 4 elements, and I'm just going to pick A, B, C, and D to be assigned to those 4 elements somehow. So that I chose 1, 2, 3, and 4, and then I permuted them with these outputs. And now I'm going to take the other 3 elements and assign them to anybody I want. I'm going to explain why that's not valid. Okay? Question?
Isn't it because it's just the one case? There's other cases we have to accommodate to where they go in the same one, the last 3.
Yeah, let me explain it my way, and then I'll take other ideas. Those kinds of I'm not sure I quite follow that. It might be the same thing I'm thinking of. I just I can't quite tell. Let's say that in these 5, 6, and 7, let's say that I send them all to D. Let's say I send them all to D. So there's a function, and it's onto. Great, we countered it. Okay, but now the problem is that we had already assigned 4 to go to D. What if I start over again? 5, 6, 7, and A, B, C, and D. What if I do this? 1 goes to B, 2 goes to A, 3 goes to C, 7 goes to D. So now I had 7 choose 4 ways to pick these 4. I did it. I then permuted those 4, and now I have, 3 more choices for the 4, 5, and 6 this time. and I decide to send 4 to D, 5 to D, and 6 to D. So I do this again. Right?
It's the same.
We ended up with the same function, but how many times did it get counted? Twice. Because it was counted once here and it was also counted here separately, because here we counted it as part of the, I chose 1, 2, 3, and 7. I'm sorry, 1, 2, 3, and 4 as the first 4 things that we're gonna make it onto. And then I did something with 5, 6, and 7 at the end. Here, I did 1, 2, 3, and 7 as the first things that I chose, and then went back to 4, 5, and 6 later. I'm still seeing this fallacious logic a fair amount in this class, and it's very common. So go back to the poker hands where I say I want poker hands with at least 1 club. Right? You have to solve that with the subtraction trick, just like you have to solve this with the subtraction trick. The reason is that if you just say, well, I'm going to choose a club, and then I'm going to take the rest of the cards and grab 4 more of them. I'm sorry. The rest of the cards would be 51. If I say I'm just going to choose a club and then I'm going to choose 4 more cards, right? If I happen to choose additional clubs here in the 51 choose 4, then somehow the first club that I chose is special compared to the other clubs that come later. Let's say you decide to stamp a gold star on whichever club you picked first, right? So the gold star ending up on the 7 of clubs here, and then later maybe you picked a few more clubs, right? That should not be counted as a different hand than if you picked, let's say, the 10 of clubs here, and then later the 7 of clubs showed up over here. This way, the 10 of clubs would have the gold star on it. It's not supposed to be a different poker hand, right? But you're counting it as different. If I said, how many poker hands have at least 1 club in them, assuming there's a card with a gold star on it, and we keep track of which card that is, then I would be okay with this answer. But otherwise, this answer is too big. This is too big. If I say how many poker hands have at least 1 club in them, we are over counting here because we're counting some hands that have multiple clubs several times. Okay. So we've got to be careful about that. So let's go back to this problem here. And I think what Fernando suggested, or somebody was suggesting, that we use the subtraction trick here. I'm going to use the subtraction trick to solve this problem right here. Okay, so I'm going to take the total number of functions, which is 4 to the 7th, and I'm going to subtract violations. Guys, if this is all you write down on your paper, right, I can give you credit for this, right? So let's say what I'm trying to say is, if you're running out of time at the end of the exam for whatever reason, I mean, I'm hoping you're gonna have plenty of time, but you never know how things are gonna go, right? If you're getting to the end of the exam and like, I don't have time to solve this whole problem, but I at least want Dr. Hammond to know that I understand that I have to take all the functions and subtract the violations. You should write that down. I can give you points for that. I'm not gonna give you full credit for it, but I can certainly give you something for that, right? So then the violations would take a little more effort, right? So for the violations, we would have to create scenarios of what kind of violations could we have. So what would be the violations? Functions that are not onto, and how could a function fail to be onto? Christian?
We have like 3
Oh.
cases where we have a case where only 3.
You
3
don't-
of our elements of X are used, and then the case where only 2 are used, so different minus.
That's an interesting way of thinking about it. So we could imagine non-onto functions having a codomain that misses 1 element or 2 elements or 3 elements. I might be willing to come back and explore whether we could do it that way in a minute. I had a slightly different way of thinking about it though. Yeah, Jasmine?
Would it be like A does not have a pre-image, B doesn't have a pre-image, C doesn't have, and then D.
Exactly. We could imagine, well, what are the functions that don't hit A at all, right? So G from Y to X such that with A not in the image of G. Okay, so those would be all functions where A isn't in the image. So that will not be onto, and we definitely want to subtract any functions like that. A second case would be the set of functions with B not in the image of the function G. And then C would be similarly, I'll just put a little C there, and then D would be this one here, right? And of course, we could have multiple violations because we could have functions that are missing more than one of these outputs. But the violations would be what set in respect to A, B, C, and D that we just created?
The union, right?
Somebody in the chat, sorry, I didn't.
know.
The
Oh,
union.
Yeah, exactly, the violations are just the union of A, B, C, and D. And so I like to frame the inclusion exclusion principle with sets whenever I can, because after all, the statement of the inclusion exclusion principle is grounded in a collection of sets. So it's nice to set up the sets, and then we're gonna try to look at the size of this union. Okay, so let's just do this. Let's see if we can do this fairly quickly here. Size of the union. Remember that we start by adding the sizes of the individual sets. So how many elements are in capital A? What's the size of capital A here? These would be functions that don't hit A at all. Basically get rid of it. And I don't care whether they hit B, C, or D or not.
3 to the 7.
3 to the 7th, right? 3 to the 7th. You have each of these inputs has 3 choices. So you'd have 3 to the 7th. And we have 4 of those. I'm gonna write it out as an addition 4 times, but you could put a 4 in front of it if you wanted. And then I'm going to subtract the two-way intersections. Right? So remember the signs alternate depending on how many sets are being put into that union. Okay, so I have to subtract the intersection of A and B. How many functions would fit that category? Louder? 2 to the 7th, right? Because now I'm only looking at functions that have only C and D for the outputs.
Do that 6 times.
And I have that 6 times. Exactly. And again, I don't care what these numbers are. Don't worry about that. And then I have to go back and do addition again. And I'm now going to add the 3-way intersections. So for example, A intersect B intersect C. That would be functions where none of little a, B, or C is in the outputs. So how many functions would there be?
1.
Just 1, right? You'd have to send everything to D. So there'd only be 1 of those. And we have 4 of those, right? So we add 1 4 times, right? And then now we subtract the 4-way intersections. How many functions are there that are in the intersection of all of these?
0.
It's impossible, right? It's impossible because you have to have arrows coming out of the domain, and they have to go somewhere into the codomain. So you have to have at least one output somewhere. So it's impossible. It is impossible to have a function that is in the intersection of all 4 sets. So this would be an answer, and then your final answer would be to simply take the total, which was 4 to the 7th, and subtract the violations. And now I think I will just combine these together. So I'd subtract 4 copies of 3 to the 7th, and I have to add back 6 copies of 2 to the 7th, and then subtract 4. And you could leave it like that. Questions on that?
I feel like if I would be doing this on the midterm, I would be doing it the way with what I said, where I would think about like the entire amount and then start like adding,
The amount of elements that are hit in the codomain.
Yeah.
So let's spend just 5 minutes or less. I think this was actually, Christian, your idea. Of instead of creating the sets like this, could we have done it a different way where the violations were categorized according to how big the codomain was, not whether a particular element was or wasn't in the image, but rather how big the codomain was. So what we could do, I'm gonna go ahead and I have not thought about this before, so I don't know how this will go, but I'm willing to think about it for a moment. So we could have violations where the size of the image of G is exactly 3, or the size of the image of G is exactly 2, or the size of the image of G is exactly 1. And we could ask ourselves, well, how, and in this case, yes, there would be no, the nice thing about this is there would be no inclusion exclusion, because you would not, you can't have a function that fits into more than one of these cases. So there's no intersections. So you wouldn't be doing all this adding and subtracting and adding and subtracting. The question is, can we count each of these cases directly? Can we effectively do that? Let's look at this one first, because I think it would be the easiest one. So one violation would be all of the inputs go to the same output. Now that seems pretty easy, right? I send all 7 elements to A, or to B, or to C, or to D. So this should have, let's just, by the way, let's just call this capital A, capital B, and capital C. These are my violations. There'd be 4 things in there. Right? There'd be exactly 4 things in there.
All right.
Yeah, that actually lines up nicely with the approach that we solved it with a moment ago. Now, let's look at functions that have an image with exactly 2 elements in them. Okay, so what choices would we have to make to create a function that has arrows going into exactly 2 of these functions?
Which X we're gonna use and which Y's are gonna map to those X's.
Okay, so which elements of X, let me put my A back in here. We would have to choose 2 of these 4 outputs that actually get realized. So that would be something like 4 choose 2.
Mhm.
Okay, so this would be to choose 2 of these, and let's just, for the sake of conversation, let's just say I choose A and B. So what we're saying is, we're now going to ask ourselves, how many ways could we make a function that only hits A and B? So in other words, C and D are off limits.
Mhm.
So now how many choices would there be?
There'd be 2 to the 7, 2,
2 choices, 2 choices, 2 choices, 2 choices all the way along the line. However, what if every one of those 7 elements picked A? That's actually something we already counted down here. So the thing that's tricky about this setup is you actually have to make sure that both of those outputs get used. So what you could do is you could say, well, I can handle that. I'm going to do my 2 to the 7 thing, and then I'm going to subtract. So I'm doing a little mini subtraction trick. I could subtract the cases where all 7 of the elements pick A, and then I can subtract also the case where all 7 elements pick
So
B.
2.
I'd take that out. And that would work. That would be okay. So you actually are doing a little subtraction trick within this case. Okay, so we could do that. Now let's look at this one.
You have to pick which 3.
Okay, so 4 choose 3. I gotta choose 3 of these 4 elements to definitely get hits. Let's say that D is off limits. So all of these elements have to hit A, B, and C, but we have to make sure that they actually all get hit. If we're gonna set up our sets this way, we would have to make sure that, so if we just do 3 to the 7th, that's not going to be good, because we might have some of those 3 to the 7th are going to be functions that only have an image with 1 thing in them or 2 things in them. So we would have to again subtract violations. We would have to subtract violations where not all 3 of these get hit. And now it's actually a little messier.
Yeah, because when you have to subtract the B part.
Because you could hit, yeah, you could hit, you see what I'm saying? So you take all of these 3 to the 7th, you subtract the ones that maybe miss C,
Yeah, so they're only hitting 2.
maybe 2, maybe only 1.
Yeah.
Right? So you could subtract like, well, that would be like 2 to the 7th, and there would be 3 choices for which one you left out,
Yeah.
but then you're actually over subtracting the cases where like You see what I'm saying? Why is this?
Yep.
So it is doable. It is doable. We actually could figure that out. It's like another little inclusion exclusion within the bigger inclusion exclusion. So I invite anybody who is bored to actually figure out what that's supposed to be, calculate this, and make sure you get the same answer as this. You can check with a calculator and make sure that it actually is going to work. Okay, but I think this is harder just because actually figuring out the sizes of these sets, even though they don't overlap, and we don't have to do inclusion, exclusion on A, B, and C, we just have to add up their sizes. We have made these sets so, yeah, they don't seem complicated, but they're just hard to count directly, right? Because there's still, subtle violations here that have to be addressed. Whereas these sets that we did originally are very easy to count directly.
Feel bad for even like bringing up the idea of that because I think it's so hard to like recognize.
Yeah.
When you're gonna overcount. Like, I feel like I've come across that mistake a lot.
It's not that uncommon. And I guess what I'm gonna say again is, guys, you don't have to jump to the first thing that goes into your head, right? Give yourself a moment to first of all, you have to make sure you understand the question. In combinatorial, that's a big deal. Are the objects distinguishable or are they identical? Am I allowed repetition or not? What about, does the order matter or not? Like pausing long enough to think about those questions, maybe even jot down some of that, because let's say that at the end of the day, you kind of end up getting a little muddled up in the solution. If you've written down some of those initial thoughts, that actually could be something I can give you some credit for knowing, right? So try not to view this as a all correct or all incorrect type of exam. Like, I don't want you to think it's whatever this number is, if it's not that, it must be totally wrong. No. I can give you credit for your knowledge of pieces of the answer, ideas for the answer. If you recognize that you're going to be doing the subtracting violations, tell me that that's the way you're thinking about it. But also giving yourself permission to, let's say this was the first thing that came into your mind. You start working this out, you realize, I don't think Dr. Ann would want me to do all of that. I wonder if there's another way to think about it. What I would probably do, by the way, if, let's just say that happens. I'm really just talking about test taking strategy, guys, because half the time, and I hate to say this, but it is really true, that a lot of times student performance on an exam is not necessarily correlated to how well they understand the material, how hard they worked, how good their habits were, and all that kind of stuff. So half the time it can just be the test itself, like how it hits you, your perspective on a particular problem. So what I'm trying to do is give you ways to mitigate issues of just the exam itself. Did you misunderstand the question? Did you misread the question? Did the first thing that popped into your head, maybe it was this, it didn't work out, but at least, you can tell me kind of what your approach is, right? So, but my point is, try to be writing stuff down. Most people did a good job of that on the quiz. Try to tell me, like, what is your reasoning? What does each thing on your paper represent? The more work you show, the more I can justify credit towards your solution. So it's actually kind of a big deal. Okay, and that way you don't have to feel so stressed about it. It's like, oh, I'm either going to get this all right or all wrong, and that's the only two choices. No, definitely not. Definitely not. Okay, so try your best to just communicate your thoughts. Okay, that is number 2. So we've done that example. Let's do another problem. Let's move on over here. Is everybody ready for the pigeonhole principle?
See, that's the one where it's like.
I didn't really do a lot on this on Friday's review, so I want to make sure I do one now. This will be on the test. You obviously have to recognize that it's a pigeonhole principle problem. You can even write those words on the solution, and if that's all you write down, if it's actually relevant and helpful, I can give you points for knowing, oh, he knew which tool that we've built in our tool collection. He knew which tool was relevant for this problem. That's worth something to me, right? So write it down, write everything down. So
What
here
sandbox
is
are we playing?
the example. Prove
What sandbox are we playing?
that out of 217 integers, we can always choose a subset of them. We can always choose a subset of, I'm sorry, of 13 of them. A subset of 13 of them. So that the difference of any two chosen numbers is a multiple of 18. So, first of all, do you understand the question? So you have a large number of whole numbers here. And we're trying to show that we can always choose 13 of these 217 numbers somehow. So that any two of the 13 numbers, right, if we take any two of them at a time and subtract them, we always get a multiple of 18. Does that sound like a pigeonhole principle? Are we trying to count arrangements of something here? Not really. We're not being asked how many ways are there to do something. Does this look like something that would be inclusion, exclusion, or forbidden positions? So you have to think through what are all the things we learned and what does this problem have anything to do with? Because the pigeonhole principle was actually a while ago, right? That was kind of where we started off the semester. So this is, I'm just trying to go through this thought exercise of like, how are you going to figure out that this is the pigeonhole principle? If it's not about counting arrangements of something, right, then that takes out a lot of stuff we covered, right? What other things do we have had? Combinatorial proof? That's usually with like expressions that are, like n choose k, and it's usually with variables. It's usually not with just a bunch of numbers like this. So it seems like, and here we're trying to show that any two chosen numbers within this subset, right, is almost like we're choosing two things out of a box. So I like to think that, maybe it would take a minute of reflection on it. That's okay again, but after a moment of reflection or two, I would like to think that we might recognize that this is best addressed with the pigeonhole principle. Sometimes it's a little more obvious. You remember the one about the girl who was watching TV a certain number of hours, at least 1 hour a day and up to a certain number of total hours. And then there was one in the sample test about the fishing trip. And this person was catching fish, at least one fish every day, up to a certain total number. Those kind of problems.
It was a ticket problem.
Hmm?
It was a ticket problem.
Not the parking ticket problem. No, I'm not talking about that.
Mm.
I'm talking about the fishing expedition problem from the sample test. Or
Oh,
the
okay.
the watching TV
Yeah.
example from the video you watched, or there was one about working on homework,
Yeah.
a certain number of hours a day, right? There was a homework problem. Those all kind of read the same. And you can recognize, oh, this is kind of like that other problem. So, by the way, I don't have it in my list here to do one of those tonight, but I would definitely review it. If you've seen something 2 or 3 times, you saw it in a sample test, you saw it in a group work, or you saw it in a homework or in a video or something, the more times I've kind of showed you these examples, probably the more likely it is that I might ask you about it, because it must mean that I think it's a nice application. That's just a hint. Just in general.
So it's not on it?
those problems are a little more obvious. Pardon me?
I was just saying, so definitely not on the test then, right?
No, I'm saying the more times I've gone over something, the more likely you should expect it. So like let me mention the parking tickets example, that was on the quiz as compared to the Steph Curry one-on-one basketball games, which was in the group work. Those were two problems that were basically the same problem,
Mhm.
right? You've seen it a couple of times now. All right, well, I better be ready to do one of those and you want to be able to recognize, oh, that's like the Steph Curry problem, or oh, this is like the fishing expedition problem, or whatever. So a lot of the pigeonhole principle problems, right? They do tend to kind of resemble one another, or the two houses that are supposed to get mail that are right next to each other, right? So that's kind of also like the Steph Curry problem. You got 51 houses have mail out of 100 that are lined up. Prove that two houses that are right next to each other got mail somewhere, right? That's another variation of that same question. So be on the lookout for examples like that. And if you've seen them multiple times, then that's probably a pretty important theme. I'm not saying it will definitely be on the test, but certainly something I would make sure I know how to do. But something like this is maybe not quite so cookie cutter. Like, I don't know that this is, I'm not sure, maybe we have had one that's kind of like this before, but I would say this one, you really do have to spend a minute to think about it. Question, Christian?
Is when you say 217 integers?
Yeah.
Is that from 1 to 2, or just?
No, just any set of 217 integers. They could be anything.
So then, why don't we just go straight to just any 13 integers? Why do we need to choose 217 and then choose 13?
We're not choosing the 217. Somebody is giving us 217 integers. We're forced to live with whichever integers those are. And now we're gonna comb through those integers and try to find 13 of them that have this property.
I guess my question is like, why don't we just choose any 13 integers? Why do we why do we just start with the pool of 217 if they're arbitrary already?
Well, these are arbitrary, right? The 13 here are not arbitrary at all. It says we can always choose a subset. We're not saying we're going to do that arbitrarily. We're going to explain in this solution how we come up with the 13. Right? That's not an arbitrary.
So from the arbitrary 217 integers, we're choosing which 13 we want to make it work.
And we're not choosing them freely,
No.
right? We're constructing. I would actually use that word. We're going to construct a subset that has 13 integers in it. We can't just pick any 13 we want. Trust me, that probably won't work, right? Pigeonhole principle doesn't say, oh, well, you get to just make a box that has what you wanted, and immediately you have to prove that you can have a box that has the objects in it that you need.
Okay.
Maddie?
So would the boxes be the multiples of 18 up to 217, or would it be 13 boxes?
Okay, good question. Maddie's asking what the boxes should be and kind of how we might set this up. So let's talk about that. What do you guys think would be a good way to set up the boxes here?
Multiples of 18.
So the multiples of 18, so that would be 18, 36, 54,
You're better at that
72.
than I am, yep.
So you want to do that?
Yeah,
217.
I wouldn't even
18
say
or-
before, because it
Can we
could be a
just,
multiple, you can multiply them and get a multiple.
Can we group the
Oh,
217?
because it's integers. And
So you just, it's just gonna come
These
down.
look like
It's not
two.
It's not like.
Yeah, it's not gonna, it's not
Thousand.
finite.
For 18, right?
Well, that's what I was thinking, but we don't know 17. So we can't, 17 years.
Yeah, we don't really, we can't just grab any old 13 integers here. What if out of these 217 integers, I do have the integers 1 through 13. If I grab those as a subset, if I just sort of turn off my brain and just say, I'm gonna grab the integers 1 through 13 in my set, well, they do not have the property that we're looking for. They do not have the property. If I subtract any two of them, I get a
Multiple.
multiple of 18 because the numbers are all between 1 and 13.
Yeah, they're too small.
So guys, the pigeonhole principle.
That's not what
is
it's
not
asking though,
about
right?
Constructing a solution. The pigeonhole principle is not about actually creating the subset that's going to work. This principle is about proving that there must be a way. Without knowing exactly what subset it is, there must be a way of making a subset of 13 integers.
It's like on the parking ticket problem, you don't know exactly which week it happened, you
Right.
just know that it happened.
Exactly. Although this is not the
I know,
parking
but
tickets problem, but that idea of,
Yeah,
the pigeonhole principle never guarantees which box it is that has all of those objects in it.
Mhm.
So, yes.
So our boxes, well, they're integers that can't be the same, right? The integers.
The
can't
two
be all the
chosen
same.
numbers.
Like out of the 217.
Yeah, we're not repeating any integers.
Okay, so then the first box would be the first 18 smallest integers.
Okay, so
Right.
this was the original idea I heard, was to label the boxes this way, but you're wanting me to do it like this.
Not, yeah, well, it'd be like
Sorry.
A1 to A18,
19,
A1 to A18.
the first 18 integers go in the
Yes.
first
And
box.
the next one would be A18 to
But I don't think that
Like
would.
the smallest integers.
So far, I'm not hearing what I wanna hear from anybody about this problem. I'm not happy with how the boxes are set up. I wanna try again. I mean, we actually need to figure out how many boxes are there going to be, right? That's going to be an issue. When we're talking about being multiple of 18, right? Of course, none of these numbers might be a multiple of 18, right? Then maybe none of them are. The issue is gonna be about the differences of two chosen numbers. So
Dr.
the way
Andy?
you wanna set this up, sorry, Fernando?
Is it that the difference is divisible by 18? Is that what we're trying to get at?
Yes, the differences should be divisible by 18, which is another way of saying a multiple of 18. But my question is, how do we wanna set up these boxes? And I'm gonna just tell you.
Could we do it by
Put you out of your misery. Yes, that's more like it. Equivalence classes. You have 18 boxes. What you do is you label the boxes with the remainders. That you can have, if I divide by 18, right, I can have any of these remainders from 0 to 17.
Been a while.
It's been a little while. Okay, so
Since you're
set up, and you should explain how you're setting up your boxes. So set up a box for each possible remainder modulo 18. Everybody's seen modular arithmetic, I assume,
Yes, sir.
at some point or another. Math 302.
Not
specific
Fernando
names.
though.
Okay, so we have 18 boxes. And what do you think the objects are going to be? The integers, which we have 217 of, right? Exactly, so we have 217 objects, which are just these integers, and again, we don't know what the integers are, they're given to us, we have to live with it, whatever the integers are that we have, and how are we going to put objects into boxes? So when you're doing a pigeonhole principle, please tell me, what are your boxes, what are your objects, and how are you putting an object into a box? That would be a great way to do it.
Doesn't the pigeonhole principle state that each box needs to have at least one? Because of like, since there's more than since there's 19, more than 19 boxes, so we know that each box will have at least one. and
Yeah,
then-
that's the basic pigeonhole principle. If I have more objects than boxes, then some box has more than one object in it. But before I get to that, I need to know, how am I putting objects into boxes? Kristen?
So what we can do is, if we have a box with 18 objects, we meet our quota, right? Because if we're gonna do is put 12 into each box. And then when we get that, when you put 12 in each box, and that will be 216 objects placed. And then when we get to that 217 one, that's our pigeonhole.
Like worst case.
But how do, yeah, sort of worst case scenario, but how do I know? I'm still not getting the answer to my question, which is how do I decide how to put an object into a box, right? So I want to put 12 in each box, but I can't just pick up an integer and say, oh gee, I think I'll put this in the 5 box. You know, here's another integer, I think I'll put that.
So,
in the 9.
Oh,
I need to know
based
how
on
are
the
you,
remainders, you do it based on the remainders.
there we go.
Because if you,
There
if
we
you
go.
have the same number with that's in the equivalence class of 1, then when you subtract them, you get a multiple of 18.
Beautiful. We place each integer into the box that is labeled with its remainder. Modulo 18. So in mod 18, those are the possible remainders. Okay.
I think the thing that you make, I guess, maybe. I just, not sure how we would guarantee that they're not all just coincidentally,
In the same box?
yeah.
Oh, if they're all in the same box, we're gonna be real happy.
But we're also choosing which box they go in.
We're gonna be real happy if they're all in the same box, because then all those integers, their difference will be a multiple of 18. So
Yeah.
any two objects that are in the same box, my friends, any two objects in the same box have the same remainder
Divisible
mod
by
18, which
18.
means that their difference is a multiple of 18. Sorry?
Now it's divisible by 18.
Yeah, that's exactly right. So, how does 217 relate to 18?
Well,
So worst case
217 relates
scenario.
to 13.
Worst case scenario, if all 18 boxes had only 12 integers in them, how many integers would that be? You may have to do this kind of back of the hand calculation on the test. Oh, 216. Okay, so we have enough objects that at least one box must have at least 13 objects in it. Okay, so since 18 times 12 is 216, which is less than 217, then by the so-called strong form, I'll let you guys review in your notes if you need to from the videos at the beginning, the strong form of the pigeonhole principle, there exists a box, and we don't know which box it is, but there exists a box with at least 13 objects in it and can make a subset from any 13 of those objects. So we can, there might be more than 13. As Nikolai said, maybe all of them are, maybe all 217 integers are in the same box. But for sure, there's at least 13 of them in one box. And we make that as our subset, and then because they have the same all 13 of those integers have the same remainder when we divide by 18, that means that their difference is a multiple of 18, right? So yeah, go ahead, Jose.
So I just thought of this, but on the midterms, is there a possibility of asking the actual proof of like the pigeonhole? Or the,
Oh, probably not for the pigeonhole principle. That's kind of just, I
He
don't know what
doesn't
the proof
usually
would
ask the
be.
proofs of the theorems. Like more, how do you put it into practice?
okay,
No, he wants to see if you can do it or.
Yeah, I probably,
I was just asking.
I probably wouldn't do that. Yeah, the question was, would I ask you to prove the pigeonhole principle on the test? More likely not. I would be more likely to ask you to use it to do something, like this problem here.
Yeah.
The difference of any two numbers in this subset is a multiple of 18. Okay. Another thing you could do if you're having trouble kind of wrapping your head around this problem would be to actually try an example. Like, take maybe you may even make the number smaller just for practice, like maybe instead of 18, choose something like 5. Right, and then you say, okay, well, what if I had, you know, a few
Seven.
integers? I wouldn't choose 217 integers, but let's say I had a bunch of integers and I was looking for multiples of 5. Then you would just have sort of 5 boxes and you could figure out, okay, here's the natural way to put objects into boxes. Okay, great. So I'll leave it at that for now. Let's go to another problem. I'm going to,
For the extended one, it's just like you have like inequalities, right? Like 2 different inequalities, right? And then, right,
I don't know what you're asking.
for the extended one, it's the inequality
right.
portion. But we would have like 2 qualities and then we have another one. And then like by the pivotal, like they would have to be somewhere in the middle. Yeah, that's common.
What's the,
Trying to figure out what he's
Extended.
talking about. Yeah, there's a bunch of notation, yeah.
study the exact 13 from this day and this day. I think that's what makes it.
I'm just gonna refer you to this thing and then let you look it up. So there's. Yeah, if you go to page 74 of the book, it's all written out. There's the strong form of the pigeonhole principle is theorem 3.2.1. And then there is a corollary here, 3.2.2 as well. It's really,
Just refreshing.
yeah, no, that's good.
We have 3 of the pigeonhole.
There's different variations of the pigeonhole principle, so that's a good point. Let me just state the one that I think is most likely that we're using here. Which is corollary 3.2.2 in the book. And again, this would have been something you would have watched on my videos before we started the formal class. So it says let n and r. Jose is just asking me to remind you about what the statement of this result is. So what it just says is that if you have n boxes and every one of those boxes has r minus 1 objects in it, and then you add one more object, right? If that many objects are distributed
That's
to n boxes,
I think so.
yeah.
then at least one box has at least r objects in it. Right, so in this example over here, the n was 18, right, in the one we just did, and the r was 13. And so we took, we got 18 times 12 plus 1 happened to be exactly 217.
Okay, yeah, okay.
Keep in mind, by the way, though, I don't have to just make this 200, I don't have to make this number exactly have this form because I can always make it larger. I could have said we have 219 objects or 225 objects. It's still exceeding this amount, right? Yes.
The kind of like backwards would be how many integers do we guarantee this will happen, right? And it's let's say 217 basically worst case scenario to guarantee it.
Yeah, right, to guarantee that a box has 13 objects in it, we could imagine, this is why I wouldn't ask you to prove this corollary, because it's just kind of common sense. Imagine that every box had only r minus 1 objects in it. Then you could only have this many objects before you overflow that box or some box to have r objects in it. Yeah, so. Okay, well, lively discussion of the pigeonhole principle, which is good, Okay, let me, I'm gonna erase over here. Oh my gosh, you know what, I'm forgetting, oh no, I am recording this. Okay, thank goodness. For a second, I thought I forgot to.
An hour and 15 in, Doctor. And
I know, I
when you're
guess we'll have to start over.
No. We'll be here till midnight.
I probably will be here till midnight. It's Monday night, I stay till midnight on Mondays. I could go all night.
Just not coming up with this. I haven't
They have
seen you on
the-
Mondays.
I just don't come in early and
Mm,
Still have the midterm to write,
I
correct?
still have to write the midterm too. So, right, I got a long night ahead of me. Evaluate the summation k going from 0 to n minus 1 of -1 to the k times n choose k plus 1. Okay. So
What's a good balance?
practice this a little bit. Everybody see that there? So let's think about this. This is, you know, similar to some problems that we've seen before as well. Any thoughts about what the topic might be?
I know.
I know.
You can definitely see binomial coefficients in here. So would there be a decent place to start? How about the binomial theorem, right? Which is like one of the most important theorems really in the entire, not just combinatorics, really in the entire undergraduate math curriculum.
in the world.
In the world. So I would recommend that you know this theorem for tomorrow. And I will write it down here because we're gonna try to use it. And if you have a thought that you might want to use it, I would start by just writing it down because I can give you points for knowing it, right? So, you know, sometimes people will ask me, why don't you let us use a cheat sheet or write out a flashcard or something? And I'm always like, well, I want to be able to give you points for knowing that these really, this is a formula that should stay with you, really. And so if I just let you put it on a note card, then I can't really give you points for knowing it because you just wrote it down and
And she's
copied it.
That's what
So
you're gonna ask us on our graduation, right?
And-
exactly. So this is one that I hope will stay with you.
I'll see you right there.
And so there you have it. Okay, so I would start by writing that down, and even if you don't get anything else down, I can give you points because you've written, as long as it's relevant. Okay, if you write down something completely irrelevant that you just happen to know about, I won't be help, you won't get anything for that, but as long as this is
Should we
relevant to the
write the
solution.
jellyfish don't age?
Yeah, right. Yeah, okay, so, what do you suppose we're gonna need to do with the binomial theorem?
We're gonna have to fix that. Adjust. So we're gonna have to-
Think maybe, derive it, so we get the n minus 1. If we
Take the, oh, because this is a summation that doesn't include n.
yeah, so like.
Okay, so we can plug in a number. So the y equals -1 seems kind of natural because we have a -1 to the k here. And we see that that would become -1 to the k. So we can do that. Let's try to plug y equals -1. So that will give me, and this is a little bit experimenting. We don't quite know. That's another thing I always like to remind people about tests is don't worry about it if you don't see the whole solution right when you start thinking about it, because it might take a minute to sort of do the step-by-step process. So that involves, what we did so far is we plugged in something for y. I would also offer that at some point, we will probably want to plug in something for x because, you know, we don't see x up here. So both of the variables should eventually disappear from our solution. Any thoughts here, Christian?
I might be wrong, but it
Okay.
kind of feels like to me that we've taken out from up there, we've taken out the first term from the binomial theorem and the last term. Because we're not going all the way to n, we're going all the way to n minus 1.
Right.
And our counter for k starts at k plus 1, which kind of feels
So
like
it's-
we'll be.
Still start at k equals 0 from the summation.
Yes.
So we are only one less term here than we have here.
Yeah.
The term that we're missing up here is,
The n.
well, the n, and you can see why. It's because if k was equal to n, then you'd be having n choose n plus 1. And that number would just be 0. So actually, if you changed this n minus 1 to an n, it would literally not change what the sum is. Because you'd be adding a term that was just 0. So it wouldn't be wrong to just kind of blow that off and say, well, I'm just gonna change the upper summation limit to an n. Because it doesn't really change the value, and then it would match up with this. Now, that doesn't fix the fact that this says k and this says k
K
plus
plus
1. Is there a way to get those to line up better?
Yeah.
You know, you can shift the index of your summation.
Yeah, that's what I was thinking, right?
So like, for example, what you could do is you could say, well, you know, I'm not going to run k from 0 to n minus 1. I'm going to run it from 1 to n. And then what you would do is you say, okay, well, when k is 0 here, it should match up with what happens when k is 1 here. So, right, so you would imagine something like this happening. Then it would look like that. Now just check that out. When k is equal to 0 here, you get n choose 1. But when k is 1 over here, you get n choose 1. Right? When k is equal to 3 over here, let's just pick a random number. When k is equal to 3 over here, we get n choose 4 with a minus sign. And when k is 4 over here, I still get n choose 4. What did I say? When k is 3, we get n choose 4 with a minus sign. Over here, though, when k is 4, I get n choose 4 again with a minus sign. These are the same. These are the same. Now, we're still one term short here compared to how many terms we have here. But just so we are aware of that, we could do that. Now, we just went to a lot of trouble to get this -1 to the k right here by plugging in y equals -1. So doing this shift here is actually taking me a little bit away from what I have on this side. So, sorry, we sort of took over.
Oh, no worries.
Okay. I was gonna say, you can sit in my office. if
She
you
wants to do combinatorics again. Come on,
Yeah.
Ashley.
Anyway, so that shifting idea is certainly valid, but I'm not sure if we really want to do it yet. Because I like this -1 to the k and this -1 to the k. Do we know what we want to plug in for x yet?
1. Maybe.
I'll try 1. Okay, somebody in Zoom is offering 1 with a fair bit of confidence. So I'm gonna put in 1 into this and just see. So, and actually, you said you wanted to take the derivative.
That would, yeah.
If I saw like a k here, or yeah, something like that, I would be totally convinced. Yeah, at this moment, because I see that, yeah, if I take the derivative of something with a k in it, then it. Yeah, so let's just see what happens when I plug in 0 for x here. Then I'm gonna get a summation from 0 to n of n choose k, sorry, plug in 1 for x, and we just get this literally like that. Okay, well, that really is close to this, right? And so it's equal, now we actually know what this is equal to. It's just, this isn't quite what we want, but we are really, really close. We were, in fact, we had it written down a minute ago. I'm gonna write it again. Summation k from 1 to n of -1 to the k minus 1. This is a shift that occurs, right? So this is literally equal to that. Term by term, totally lines up, okay? So comparing this one with this one, to ask yourself, what, is there anything we could do? This is what we already know is correct. Can we do something with this that would make it look more like what we're being actually asked to evaluate?
Do we take out the k equals 0 term? So that would start our summation at k equals 1.
Okay, we could take out the k equals 0 term and choose 0 as 1, -1 to the 0 is 1, so we would have a 1, and then we would be adding k from 0 to n, sorry, we just took out the 0 term. 1 to n of n choose k times -1 to the k. So we could like just literally pull out the first value of k from everything. And now, how is that looking? So if I just solved for this, what would it be equal to? Zero.
-1.
-1. I have to move this one to the left side, so just algebraically move it over. So that's equal to -1, right?
But the
Yeah,
K minus
the
one up
K
there
minus one.
flips the sign of everything, so.
Oh, so what we know is this.
flip-
And how is it different from this? It's off by a minus sign. It's off by a minus sign, and so what I can do is I can take this, multiply it through by -1. Multiply it through by -1, and I get -1 to the k plus 1 or -1, doesn't matter. And if I multiply on the right side by -1, I get a 1. And now, my friends, that is literally what we were being asked to evaluate. And so this is the answer. It's equal to 1.
So would a good strategy be to do that top equality first? So just see if you can make it look like anything that might jog your memory, and then go into the maybe plugging in y equals -1 and all that.
I know I'm gonna need to plug in, so let's talk about, kind of reflecting on this now. I know I'm gonna need to plug in numbers for both x and y. That's because there are no x and y there are no variables at all up here other than the fixed n value and k value that are fixed, okay, so that are already established in the question. So I'm expecting to plug a number in for x and I'm expecting to plug a number in for y. Now, in this case, I don't see anything here other than the binomial coefficient with a sign attached to it. If I saw like a k down in front, or maybe even there was more than that, or if I saw a 1 over k, right? I think you had some homework on this where you actually had to do a derivative or an integral before you could like evaluate the x or the y. That is something we have seen before, right? So we have seen that kind of scenario where you have to take the binomial theorem, plug something into it. I mean, so for example, we could have said, well, let's take the derivative here. And take the derivative. It would look like this, right? We can certainly do this. It's from 0 to n, and choose k. And so if we differentiate this, this is with respect to x now. N minus k minus 1 times n minus k minus 1 times -1 to the k, right? What's the difference here? Like, after you've taken the derivative of your binomial theorem, you're going to see not just the binomial coefficients, but other scalars multiplied out in front of it that are indexed by the k value, so that each term has a different scalar in front of it. That's kind of a clue. So I would recommend, like, if you go back to the problems in chapter 5 on this, you're going to see a few of those proofs, and you did them in the homework where you had a summation that had some coefficients in front of each term that had some regular coefficients in addition to the binomial coefficients. This problem doesn't have that. This problem just has the binomial coefficients with a sign attached to them. And a sign change can, of course, be accounted for by doing things like plugging a negative into it, right? If I saw powers of 5 in my thing I was proving, if it said evaluate, this thing times 5 to the k, then I would probably start thinking, oh, I wonder, maybe I need to plug in y equals 5, right? Because if I do that, then I'll get powers of 5 over here in my summation, right? So the way you do these problems, guys, is first of all, you recognize it's the binomial theorem, write down the general binomial theorem, and then you ask yourself, how do I manipulate that binomial theorem to be relevant to what I'm being asked? That involves plugging numbers in. It involves potentially taking a derivative or an integral. As we've seen, technically, we could do any kind of algebra. We could do multiple derivatives, multiple integrals. Anything like that would be a possibility, right? So am I
Dr. Annan?
answering? Fernando?
Is the derivative that you have on the right-hand side of the summation, should it be n minus k for the term in front of the x to the n minus k minus 1? So it should be like n minus.
Probably, yeah, for sure. Sorry, it's Monday and I'm wearing shorts, so I'm not my normal self right now. So I temporarily couldn't take a derivative correctly. Yes, the derivative of x to the n minus k would have been n minus k times x to the n minus k minus 1. You got it. Thank you for fixing that for us.
One more question.
Yeah.
So what would be like the telltale of integrating?
Oh my god.
The integration is when you integrate this thing, you get like 1 over n plus 1 times x plus y to the n plus 1. So if you see these kind of numbers, like you see 1/2, 1/3, 1/4, 1/5, 1/6, that's kind of a telltale sign. Yeah. You know how you can you guys can make your own problems up for this, by the way. You can make up one and then hand it to your friend and see if they can solve it. All you got to do is take the binomial theorem and say, okay, I think I'm going to plug in, I don't know, I'm going to plug in y equals 3. Okay, so I'm just making one up. I'm going to show you how I'm going to write my test tonight. Okay, so I put a number in for y, right? So something like that. So you'd have n choose k times x to the n minus k times 3 to the k, right? So you do that, and then I say, I think I'm going to take the derivative of both sides. Okay, so this is n times x plus 3 to the n minus 1 equals the summation k equals 0 to n choose k. I'm going to get it right this time. N minus k, x to the n minus k minus 1 times 3 to the k. And then if you don't like your friend very much, you could make it even harder on them and take another derivative. Take another derivative.
Oh, I'm gonna do this to Fernando.
So I have not done this on the, you didn't do this on the homework, right? So this would be like a natural extension. Take 2 derivatives of both sides. Okay, so now I'm going to do another derivative here. Summation and choose k. Now I have n minus k and I have n minus k minus 1. And then x to the n minus k minus 2 times 3 to the k. So now I've differentiated it twice. And now I can say, okay, now let's plug in a number for x. 8 sounds good. So I plug in 8 for x. So I have n times n minus 1 times 11 to the n minus 2 equals summation 0 to n choose k, n minus k minus 1, 8 to the n minus k minus 2 times 3 to the k. And then you erase everything except this equation. You hand it to your friend and you say, prove it. And this is what they're going to prove. And you should be able to look at this and say, all right, this is kind of like the binomial theorem. It looks like we plugged in 8 and 3 somehow. But I see a couple of scalars down in front. That makes me think that I might have taken a couple of derivatives, right? Because every time you take the derivative, the power rule pulls down those coefficients, right? So you can hand this to your friend and say, prove this equation here. Right, and see if they could do it. And
Call it by like a name too, like what's the differentiable penumbrum theorem.
Fernando's theorem.
Yeah, Fernando's theorem.
yeah, you can name this. You can make your own equation and then make it a theorem that's named after yourself.
Yeah.
There was a professor in our department once, I don't know, maybe you know the person who actually had the students write the exam. Basically, everybody in the class wrote a question and then just gave it to the professor, and I think he just picked out the questions. Like, we could literally do that, like 30 of you could each make up your own equation and, you know, share around ideas and stuff, and then we just put one of them on the test and
Don't
that's
give
the question.
Nikolai and Fernando
Something
ideas.
really-
It's just
Let's do it. I like that idea. Let's do it.
No.
I think
I'll do,
somebody
like,
did
10
it. I
derivatives or
think there
something.
was a professor in our department who did that once. But anyway,
But
seriously,
then
with a lot,
answer.
also with combinatorial proofs, right? You can figure out what scenario do you want to have. I have a committee with a president and a vice president. And maybe there's some condition on those people, like maybe you have males and females and you make certain
It
rules.
sounds
right?
like a combinatorial proof.
You can do that. You can like create a scenario and say, well, here's how many ways there are to do that, and then here's how to represent it using combinatorial binomial coefficients, for example. So I actually,
Either.
I don't say this about most of my classes, but this is a class where like you guys not only can be like practicing answering problems, you actually could be making problems. You
But
could,
also, who would come up with the answer?
well, you should come up with the answer
No, because
while
I
you're
feel
solving it.
like about this, right?
While
You
you're
realize, like,
creating
I thought about it this way, but then actually this.
It's all
So-
good. You're gonna learn from all of that discussion. It's gonna be great.
I'm trying
Okay.
to think of a professor who did that, 'cause I feel like.
I think there was somebody who did that. I can't remember who
But
it was either. Oh, okay. So, now it shows one students.
Yeah.
Okay, I kind of think I remember that too, but I don't remember who it was either.
So I. Oh, that's nice.
I'll let him know you said that.
No.
Okay, let's go on to something else, unless there's any, are there any questions about the binomial theorem here? Okay, let's try, we're almost done, guys. No, not that many more to go, just a couple more problems here. Let me do number 9, and this is,
With
Um,
bagels.
this is with bagels. So we have a bagel shop.
This makes me hungry, Dr. Anian.
Well, then that's why we're doing it towards the end of the review.
Go get bagels.
Has
Have fun.
flavors. I'm gonna write down the flavors here. We have onion. I really don't like that.
What do you get bagels?
Poppy seed, I like those.
They hit.
And then we have egg bagels, salty bagels. Pumpernickel.
Where did you get these?
I probably went to a bagel shop one day and wrote down all their
And
flavors.
Blueberry was like
Sesame.
not there or what?
Well, I have enough to already write my question. Raisin and then plain. So those are the 8 types of bagels, and then the question is, how many ways are there? How many ways to choose 6 bagels? So guys, if there's any question about whether the objects are supposed to be interpreted as distinguishable versus identical, be sure to ask me during the test. I'll definitely do whatever I feel I comfortably can to clarify the question for you.
So for
Is it a given if, oh, I've just noticed that you'd say identical to specific or, but.
I usually would say identical, although here, you know,
they're bagels, so
these
Yeah.
are just bagels, so they're kind of identical, like every plain bagel looks like every other plain bagel. So, if they weren't going to be identical, then I would have to like. You know, at that point, it wouldn't matter that we had all these different
Interesting,
flavors.
cause I wasn't thinking they're identical, it's not like, oh, they're different, right?
There's different kinds of bagels. But within each, it's just like there's different kinds of penguins on that quiz question, but then within a particular type, all the Gen 2 penguins were either distinguishable or identical, right?
So for the first part of this, because all the bagels
I
are
got
the
that.
same, why don't you
Yeah.
just do, you have 8 stars, because you have 8 different types of bagels. Wait.
You would want 6 stars, right? Cause you're choosing 6 bagels and you have 8 different
Six.
categories.
Yeah, so there's
So then you
6
have 7
stars.
bars.
How many bars?
Who said it?
7 because you have 8 kinds minus 1.
Beautiful, right, so there's 7 stars, those are the bagels. And then there's 7 bars. And I'll just say that separating the 8 kinds that we have. We have 8 kinds of bagels and we're using 7 bars to separate them. So I'm assuming that that order does not matter here. The order in which we choose these bagels, we don't really care about that because we're just going to put them in a bag and carry them out with us, right? Order does not matter. Also, repetition is allowed because I can choose the egg bagel many times or the sesame bagel many times. At least with the information we have here. Now, if I said something like the store only has 3 plain bagels left, well then that's a constraint that we would have to subtract violations from. But here, we're just going to set up an equation. I like doing it this way actually, where you actually make variables. For the 8 different kinds of bagels, and you have a total of 6 of them chosen. So you'd get an equation that looks something like that. And the answer then, well, what's the answer gonna be?
13 choose.
Stars plus bars, choose bars. I usually choose the bars because the bars usually doesn't change. But it doesn't matter, you can choose the bars or the stars. And so we get 13, choose 7. Okay, so then that's just the first part of this. Yo.
Why not 8 to the 6th power?
8 to the 6th, so that's gonna be putting things in order. So that would be like, my first bagel is a poppy seed, and then my second bagel is a pumpernickel, and my third bagel is a pumpernickel, and my fourth bagel is a raisin. And you actually have slots with 8 choices for each of the 6 bagels, but now you have a first bagel, a second bagel, a third bagel, a fourth bagel, a fifth bagel, and so on. And that is putting an order in when we don't want order. That's really the reason.
Yeah.
That's like license plates, right? I care about which thing was first, second, third, fourth, fifth, and sixth.
Yeah, I agree. Yeah, that's.
Plus it's the whole like combinations of multi-sets.
You know, I should probably start off by saying the first thing I would have written down on this problem is order doesn't matter. Because again, you can get partial credit for telling me that you've paid attention to these important issues. So order does not matter, repetition is allowed. And then you can remember from our little rubric, I know the rubric isn't perfect. Not every problem has a clean-cut answer to the order and repetition questions. But in this case, it does. And this is exactly the scenario for stars and bars. Good enough? Okay, now there's of course I have a part B. You should expect these multi-part problems. The only thing is I will not penalize you from one part to another, right? So you should just take whatever answer from one part. If you're going to use it on another part, that's fine. So here is part B. Part B of the same question. A dozen bagels. So this time, how many ways are there to choose a dozen bagels? So that's 12. 12 bagels with at least one of each kind. Thanks. A dozen bagels with at least one of each kind. So
This is like the fruit problem where we just take it out,
Well,
get rid of those 8.
yeah, so we take out we're gonna take 8 bagels automatically because we're gonna grab one of each kind. Again, I don't care what order anything is done in here. So I'm just gonna grab those 8. So we just remove 8 stars. Another way of saying it would be we want to, so we could just subtract 8 from, basically you could subtract 8 from the, oh, this is for a dozen bagels, I'm sorry. So we would from 12. So we would have drawn 12 stars, but we would remove 8 of those. This would leave us with 4 stars left. And we still have 7 bars. And so the answer to the question would be 11, choose 7. Right? Does that seem, let's make sure that's what I got. It sure is. I do want to mention something about this, as long as I'm on the topic. Another way to have done this would have been to, set up our equation again. But this time it'll be equal to 12. So x1, x2, x3, they all add up to 12 this time, but we would just have this extra condition now that the xi's are at least 1. So one thing you can do, keep in mind, you cannot have a negative number of bagels. So we could think of it this way. And if you want to formally deal with this problem rather than just saying, I'm just going to remove 8 stars, you can do this by shifting the variables. So you can create new variables like y sub I would be x sub I minus 1. And now that is at least 0. Okay. So you can do that, but of course, then you come up here and each xi gets replaced by the corresponding yi plus 1. So we can do that. I would just want to show you this. So this is the formal way of doing it. So you leave the 12 where it is, but you change each of those x's to a corresponding y plus 1. And now you see that 8 times you have added 1. Right? So if I now subtract them over, I get to the same place again. I get all of my y's adding up to only 4. And so that's where the 4 plus 7 choose 7 comes from. Okay. I like this way just because you don't have to think so much. You just kind of create equations and do it all very formally. But I wanted to point one thing out. There was a homework problem recently where the conditions on these x's wasn't just 0 to 1. There was a problem on the
That's part
homework.
C.
That's part C.
Huh?
That's part C.
Part C. Cause it's the plain bagels are between the 2 and 5.
Oh, okay. Oh, okay, yeah, let's just do part C. Thank you. I'll just do part C. So, because people were doing one little thing wrong on this on the homework, so I just wanted to go over that real quick. So, and we can do it right now. So on part C, it says we still want 12 bagels with at least 3 egg bagels between 2 and 5 plain bagels at most 2 raisin bagels and at most 2 sesame bagels. Okay. So,
So we would do the. We would do like the base part first, and then we would do the most for we would do the violations, right?
yeah, so you have the at least conditions and the at most conditions. Do you see that, guys? You have both of those. Yeah, that's what Fernando's saying in the chat. We're going to start by addressing the at least conditions and then the at most conditions. I'd like to do it formally with these equations again, though. If that's okay. So we're going to imagine adding up the numbers of each types of bagels. It still has to add up to 12. And by the way, we can imagine that those X's are lined up with these different types of bagels. So the onion would be X1, poppy seed would be X2, and so on. So we can label the variables according to the kinds of bagels that we have here, and that's not a bad idea. And so then over here, we can just say, oh, at least 3 egg bagels, that would be X3 is at least 3. Between 2 and 5 plain bagels, the plain bagels are the X8. So X8 is between 2 and 5. At most 2 raisin bagels, that's X7, at most 2. And then at most 2 sesame bagels, which is X6. So X6 is at most 2. So I have a bunch of constraints here. Okay, so there's nothing too crazy about this, but we just have to not get in too big of a hurry and make a slip up. Yeah.
So you subtract it from the X8,
Mhm.
you subtract the minimum
Yes.
from all sides.
Correct. That's the mistake that came up in the homework. So people were doing the change of variables like y sub 8 equals x sub 8 minus 2, which is correct. But people were leaving the 5 over here as the upper limit. And we really don't want to do that. So if we replace y sub 8 with x sub 8 minus 2. So if we subtract 2 from x sub 8, then the limits now go from 0 to 3. Okay, so make sure you change that 5 to a 3. We don't have any other conditions for at least on the x6 or the x7. We just have x3. So I would let y3 equal x3 minus 3. And now that one's also greater than or equal to 0. Okay. And all of the other yi's, I'm just going to leave them the same as the xi's. So now X1 gets replaced by Y1. X2 gets replaced by Y2. X3 gets replaced by Y3 plus 3. X4 gets replaced by Y4. X5 gets replaced by Y5. X6 gets replaced by Y6, X7 by Y7, and X8 gets replaced by Y8 plus 2. And this is still equal to 12.
We, not
Wait.
saying 7, 6 week, or did we do?
I'm sorry?
No, we're doing the at least.
7 and 6?
I haven't dealt with this
We're
part yet.
doing
Oh,
the at
sorry,
least
sorry.
first.
Yeah, I haven't dealt with that yet. I should say this is for I not equal to 3 or 8. So not the egg bagels or the plain bagels. So we can, I guess, subtract 5 to both sides. So then you would get Y1 plus Y2 plus dot 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 plus Y8 adds up to 7. But we still have constraints here, namely X6 is at most 2, sorry, Y6. X6 is the same as Y6. Y7 is at most 2. And Y8 is at most 3. This is the problem we want to solve. This is the new problem.
We have 3 buttons.
Let's just make sure everybody's with me.
So now we have an inclusion.
Everybody following this out there in Zoom world? Oh my gosh, there's 17 things in the chat.
It's all fair, probably.
I've not been paying any attention.
That's all right, it's Fernando.
Is it?
Probably.
There's a bunch.
Well,
It's quite a little bit. Okay, anyway, I wasn't paying good attention to the chat. So this is the new problem. We've handled the at least conditions by doing this change of variables. And now we have to solve this with no constraints. If we just looked at this equation here, I have 7 stars and 7 bars, right? That's 14, choose 7, right? And I'm gonna subtract violations. Violations, well, I got 3 flavors of violations, right? The violations would be, so we could do 3 sets. I do like to create them as sets. Capital A would be choices with Y6 at least 3, right?
Yeah.
And similarly for all 3 of these. Is everybody able to see that out there?
Except for
Or
Y8.
Y8.
I'm sorry?
Y8.
Well, it would be at least 4.
Y8 would be at least 4, exactly. So C would be the set of choices with Y8 being at least 4. So we're gonna be subtracting the union here of these. So it's a bunch of cases.
So Y7,
Oh, whoops, that should be a 3. Thank you. Yeah, this is making me hungry.
Told you.
It's not the union, it's the onion.
That's it. Exactly. So we have 1427, and now for each of these violations, we can just basically subtract this many stars for each
Mhm.
one. So the first one, we take off 3 stars. See, I like to, so there's been some people who've been changing this bottom number according to how many stars there are. I prefer to use bars on the bottom, so
Because
there's
then
always
it's
just the same
consistent.
number on the bottom, yeah.
You're gonna get
And
11.
then 11 again, and then we'd have 10, right? And then the 2-way intersections will be plus, we'll change the
Seven.
signs, and now we have to add
So
2 of these, like 6 here.
you
So
get
3 and 3 is 6, so that gives me 8,
choose 7.
2, 7, and then we do 3 and 4, which is taking 7
So there's a,
away, and so that's just 7, choose 7.
and the next one, so.
The next one is also 7, choose 7, that's the intersection of B and C, and then the intersection of all 3. Remember, I'm only grabbing 7 bagels, and I have to have at least 3 sesames, 3 raisins, and 4 plains. That's impossible.
14, because you have 7 of those.
Let me just check my solution here and make sure I did it right. 14 choose 7 minus 10 choose 7, 11 choose 7, 11 choose 7, 7 choose 7, 7 choose 7, 8 choose 7. Looks good. Looks good. So I like doing the shifting here. I don't think I originally explained it that way when we were first talking about violations with stars and bars, but it does work really nicely, just for bookkeeping, and so you don't get lost in what you're trying to do. You take out the at least conditions first by converting into Y's, and then subtracting the at most conditions, which are the violations. What do you guys think?
Good reading.
Questions here? Yeah, this is just a standard problem. You should definitely expect to see something like this as well.
As well as derangements, right?
Pardon?
Derangements. Derangements, sorry.
What about that?
Yes.
As well as
derangements will be on-
Well, that's another topic. That is, yes. Derangements is another topic. The other topic that I didn't do in either review session, and I'm kind of thinking I might not do it if it's okay, because we're just about at 7 o'clock. Is the only problem left on the sheet that I have not gone over is actually number 6.
Oh, the forbidden positions?
Yeah, that one is pretty. Do you guys find the forbidden positions problems to be pretty easy to identify?
Yeah.
They're kind of annoying to do them, but they're pretty. You draw the little grid. Sometimes the grid might be given to you. Other times it's a word problem and you have to go through and put the X's in the box yourself. I do have one comment about the forbidden positions though. If you had a forbidden positions grid, and the reason I'm saying this is, let's say that you have to create the grid and you could put the one category and the column in one category across the top, right? Maybe you set it up so that the picture looks like this. Let's just make up an example, something like that, right? If you had set it up like that, I would highly recommend that you flip it. You just
Yeah,
transpose it.
because then you don't have to do 3, 4, and 5.
So put the first column in the first row and the second column in the second row, because now you won't have an R3, R4, or R5 to even do, whereas here you have to go all the way through R1, 2, 3, 4, and 5. It will take longer to do it this way. So, and see, if I give you the picture, I can make sure that it's set up more nicely for you. But if I just give you a word problem like this one with the employees that are staffing a desk and you just happen to kind of switch the time slots with the people or whatever, then it's possible that you could just innocently set up your grid so that this is the way that the picture was.
So
So I
I heard-
just wanted to encourage you to be open-minded about this, that if you set up one of these yourself, you can flip it literally like a transpose of a
then-
matrix.
So then what I heard is you're gonna be nice and just give us the grid.
Give the grid?
Yeah.
I don't know if we've done this before, but the forbidden positions only work for square meter.
Oh yeah, the forbidden positions would be always a square matrix. That is a good question as well. Can I let you guys do number 6 on your own? I have the R values. Make sure you know the theorem for the forbidden positions, right? You have the total number of permutations of n objects, right? And then technically what you're doing is you're subtracting violations. And there's, R1 violations of 1 position, so that's times n minus 1 factorial. Then you add R2 times n minus 2 factorial, and you just keep going like this until eventually you get to R sub n. R sub n is basically 0 factorial with either a plus or a minus on it. Okay, and you don't hardly even need to memorize this too well. You just have to realize that each term has 1 less factorial than the one before it. I actually would probably just kind of remember it's like this. It's dot, dot, dot. You just keep going and it works out fine. So this one that's number 6, I do have a solution in the Canvas resources, so you can try it. And if you can't get the same answer that I have, then you can definitely stop by. But I would love to take a 1-hour break to go get some food because I'm supposed to be back here at 8 and I'm gonna stay until midnight to answer questions and to help you guys out. What do you think? How are we feeling? Better?
Yeah.
You're not supposed to walk out of my review sessions feeling like you're done, you don't have anything else to do. The review session is more about trying to remind you of things that you still are maybe weaker on, right? Maybe there's something here that made you a little nervous, or you're like, oh, I need to practice more of those pigeonhole problems, or I need to practice more of the stars and bars, or whatever it is for you, right? So I really appreciate you guys coming to the review, and I will be around tonight. I will have Zoom as well if you're already at home and don't want to come back to campus, but you want to chat with me about any of this stuff. I will be around, so feel free to take advantage, or else you can catch me tomorrow, but it'll be a little hectic tomorrow. Tonight is a good time.
How long
All right.
is your final review session?
Just kind of see.
No. Thanks. Thanks for coming, guys.
No,
Yeah,
Thank you,
bye
Dr.
for
Anna.
now.
Thank you, Dr.
Thank
Anand.
it
you.
was like all weekend.